Audio might not be fully recorded. Why? Are you can hear me? Alyssa, you can hear me well, right? Yes.
Yeah, I can.
Okay. So hopefully the audio will be okay for the recording. Screen. Okay. All right. So just as a reminder, please by Friday, the second one, and then the third one by Monday, right after your spring break, so that I can open up all the key for everybody. All right, and don't forget you have an example from 2021 to review and study from, and with the key. Okay, so let's see. Just recap from the lecture, the recorded lecture, just to get you all on board before moving on with this topic. So this will be part of the exam. Supposedly exam 1 also has enzymes, but you won't obviously have enzymes as part of your exam 1. So less material to study, yay, for the exam. Okay, so define protein denaturation, simple terms.
I guess in simple unfolding of the protein structure.
That is a very simple term, unfolding of the protein structure. Very good. In technical terms, what's technically happening to the protein? Yes, Jean. Yes, so we have some bond cleavage destabilization and change in the structure. And it can be on the tertiary level, on the secondary level, and on the primary level if peptide bonds are broken. So denaturation can occur at different stages or different levels of the protein structure. So change from native structure to another type of some sort of a stable structure. Okay, how does amino acid composition affect the protein's thermal stability? What do you say? What say you, Jean?
So like a more ordered structure of data sheet or outside fluids, you will need lower denaturation temperature to break.
Yes. So the more ordered structure you have, so ordered secondary structure, a globular structure, then you will have denaturation at lower temperature than when you have an open structure like casein, for example. You would need really high temperature to denature casein compared to whey protein. But there's another thing as well. When you have what will cause stabilization?
Isn't hydrophobic residues more of them causes?
So you're very close. So hydrophobic residue causes the formation. When you have a lot of hydrophobicity, you have quaternary structure to stabilize. But somebody said something else. Not hydrogen bonding. Yes, disulfide. The Jean said it first. It's okay. We'll give Coleman that. We'll give Coleman. It's competition. All right. Okay. So again, so the amino acid composition really dictates whether you're going to have secondary structure like alpha helix, beta sheet, and also whether or not you have a high amount of protein, for example, will give you this random open structure in casein that has 17% of its amino acids in proline. So this will break secondary structure and will give you rigidity in terms of orientation and turning and forming globular structures. And then the sulfide group. So amino acid composition does impact thermal stability. How does water facilitate thermal denaturation?
Like usually if you have low water concentrate, you'll have higher energy.
Exactly. What happened when the protein is in a lot of water and then you heat? Go ahead.
Like the water can go inside the molecular to break the hydrogen bond.
Exactly. So there's swelling. So water goes inside the structure of the protein and then breaks hydrogen bonding internally, and then hydrogen bonds form with the water instead of with internal residues. So you have swelling and then facilitating with kinetic energy, facilitating the unfolding of. So the most stable form of the protein is in its driest state. Okay,
Sam, I have a question about the amino acid composition.
yes.
I know this isn't correct, but in my head, it feels like the more structure, like the more like stable or rigid or formed it would be. Why is that incorrect?
Well, there's a difference between rigid and between an orderly structure. So orderly structure, that you have an order, you have an alpha helix structure, you have a beta sheet structure, that's an ordered structure. Rigid, that means not very flexible. So when you have SS linkages, then that's a very rigid structure. And not only that, to break an SS linkage requires a lot of energy. So the SS linkages contain a lot of energy. So when you run DSC and you see that 11S has a denaturation temperature around 90 degrees and 7S has a denaturation temperature around 80 degrees. Why is that? Because 11S has disulfide linkages and 7S does not, for example. Okay. Why high protein concentration may result in irreversible denaturation upon heating? Yes, John.
Like extreme aggregation of polymerization, they polymerize in a way that they can't do that.
Yes, so when you have high protein concentration, those proteins in solution in aqueous, they're moving and they become, there's a lot of near proximity to each other. And then when they're denatured and they're close to each other due to being crowded, high concentration, then yes, then we will have irreversible polymerization happening, especially if you have disulfide and high hydrophobicity. Okay, what are the factors that influence protein structure? Or factors that cause denaturation? Temperature, right? Temperature, pH, salt. So temperature, pH, salt.
What about amino acids, like sequence?
External, I would think about external factors like solvent, organic solvents. Pressure, yes. So physical, so the protein can be denatured due to physical forces, due to changes in temperature, due to changes in pH, in salt, in solvents, also adding denaturing detergents, enzymes, absolutely. Yeah, denaturing agents like SDS and urea, DTT for reducing DTT and beta-metactoethanol. So detergent, organic solutes, and reducing agent. Okay, so a lot of factors, and we talked about in the recorded lecture a lot about those different factors. Okay. What are some common methods used to assess degree of denaturation? Hey! Your favorite DSC. Okay, great. What else? Priyansh. NMR, my least favorite. Yes. Okay. What else? What's that? FTIR tells you changes. Mostly we look at secondary structure, but it does tell you other functional group changes. But yes, FTIR. What else? Raman, yes, of course. UV absorption. Can you tell me how? Yes. Yeah, well, that's okay. So when the protein unfolds, hydrophobic groups are exposed, and tryptophan and tyrosine are among those hydrophobic residues that absorb light. So when the protein unfolds, then those hydrophobic groups are exposed, and then you have higher UV absorption and higher even fluorescence, especially if we're doing our favorite surface hydrophobicity assay, which is based on binding of a fluorescent to a hydrophobic resin. Okay, what else? Solubility, yes, your other favorite assay. So what? I didn't hear that.
Someone booed.
Booed?
Yeah.
Oh, come on. Did you boo it? So boo at Chris. What happened? What happened? Santa Claus. 2 weeks ago, you didn't have that. Okay, never mind. Was there anything else? Activity, bioactivities, where if we're measuring enzyme activity. Yeah, anyway, good. What are some, that's it, right? Yeah. Questions? Charu,
So ask questions like related to other things, not particularly this section.
that's fine.
But I wanted to know, like, if for exams, if you're gonna study like all the principles like of NMR and stuff like that.
NMR, I told you this is my least favorite, so.
And yes, like all the.
So, you would need to know whatever I said in class. But the documents I gave you had a lot more detail, and this is FYI. So if you really want to know exactly how the matrix worked in MALDI, then you read that, and I will not ask. But I mentioned it, it's based on, it tells you molecular weight, it's based on the flights, like the, yeah, simple things, common things. But I said FTIR is based on the absorption in the IR region and vibration, and you determine functional groups. So certain things I said in class is what I would expect you to know, but not the detail covered in those individual documents. These are reading material.
Okay. Can you please explain the whole fund and high volume concentration?
Yes. So when you have a solution, let's say 1% protein, and you have a solution that's 5% protein, the 1% protein, you have less molecules, less protein molecules in that same volume. And then when you heat, those proteins are denatured. So if you have a lot of these denatured proteins, like the 5% will have a lot of these denatured molecules, that means you will have shorter distances between those proteins in solution. So this shorter distance will allow attractive forces better. And once you have those attractive forces becoming stronger, because they are in near proximity, then they can form polymers. And then when you form polymers, it can be irreversible, especially if it's disulfide linkages. Then, yeah, that would be irreversible denaturation. Good. Anything else? Yes, Anastasia?
Can you explain more about, you said that enzyme can manipulate the protein.
Yeah.
So which conformation is affected more than this enzyme?
So all the conformations, because when you use an enzyme, what happens, you are breaking peptide bond. And when you break the primary sequence, then everything else is like a chain reaction. When you break a primary sequence, you're gonna remove some functional groups that cause a certain formation or configuration. So that would be like a chain reaction. You will cause denaturation.
So finally, second all are affected.
Yeah, once you start breaking those peptide bonds, everything else will be destabilized, or your secondary structure, tertiary structure, everything will be destabilized. Good. Other questions? Happy to answer anything. Yes.
I was reading like the first part of what brought about the enzyme, and I understood how like trypsin, like where it leads. But for example, for thermolysin, I couldn't understand. It says R2 position it leads.
Which one?
Thermolysin. It's in the table you gave us.
Yeah, the table. I didn't say study the table.
I was like, I don't know, I just want to check, do we have to study the table?
No.
No.
You don't have to study the table. I was just showing you the table that you have different specificities. And different enzymes might be specific to certain amino acid when they recognize that they will do. Or certain hydrophobicity or acidity that would trigger the binding. But I don't want you to remember what, metalloprotease or cysteine proteases or all of those. No, I didn't ask you that. It was just an example table. Trust me, when I want you to remember the table, I'll tell you study this table. If I don't say study this table, I will bring it in the exam for sure.
There was a
No.
question in the almost one that's where I asked. Also, the last question is, so there is, we discussed.
There was a question on
The homework one, like where plasma increase.
yeah, plasma is same as, it has same specificity as trypsin. Yeah, if it's in the homework, study it.
Next
Okay.
question is the fluorescein and OPA method we discussed for quantification of amino acid. Do they can we use both the methods interchangeably for determining the degree of hydrolysis? Because they both.
OPA and what the other?
Fluorescein.
Oh, it's a different reagent, yes. So it's based on the reaction with the amine groups. Yeah,
But we can still use both, any of it for degree of hydrolysis.
yeah, you can. It depends on, again, standards that you use and the calculation equation that you use for the pH. So, yeah. So the OPA is more common and a lot of people study it and you have a clear calculation for it. The other one is less studied for the like that.
Yeah, I have a couple questions. You said that excess pH adjustments can cause dehydration. What is considered excess though?
Well, it depends on the protein, right? So that's why I don't, when I say excess, I don't give you like 2 hours versus 5 hours. But when pH is extreme, like pH 12 or 11, that you use to extract your protein. And we do it for 1 hour, right? So when you do DSP, you see some peaks, but it has lower entropy than when you use salt extract. Because that 1 hour at pH 12 did cost some. Yeah, so that 1 hour swing, but if you put it, let's say for 10 minutes, you might not see it.
So you said it's a lot more about the time and a lot less about what that actual pH.
Both, it's a combination, so it's a compounded effect. So you have the pH and then you have the time and then also the temperature.
Okay.
So if you have temperature changes like high alkalinity and high temperature, definitely complete the pH.
Okay.
Yeah, so it's not one factor that exists in vacuum, it will be multiple factors. And
Okay.
every protein is different too.
Okay.
So that's why I like proteins, they're very interesting, they keep your edge, and you cannot just make an umbrella conclusion. I think.
Yeah, I did have one more.
Yeah.
So like, I guess maybe I wasn't clear on this, but once the protein denatures, does it ever go back to that native state?
No.
Okay.
Well, it's the reversible denaturation, so it can go back to this like short, very, very short lapse of temperature and then going back, it might reconfigure itself to that original state. That's a reversible denaturation.
Okay.
Yeah, but over time we deal with something beyond reversible.
Okay.
Yeah.
And then like when it does, okay, if it's beyond if it's beyond its capacity to go back to its native state, is the next state, like, is it random? Do they just like randomly?
Yeah, then they will find, there will be an example in this lecture, like how collagen becomes gelatin. And it is a stable form, it's fine, the protein finds another low energy state, but it's not going to be given.
Okay.
Yeah, it just finds,
It's just random.
yeah, it would, that's why a lot of it would be random oil. It just becomes not oil.
Okay.
Yeah.
I remember, you mentioned for some method, you want pure protein. So you like moldy like that. What does that mean by pure protein? Is that?
You know, take your soy protein, how many protein bands do you see? Infinite. And if you want to take the sequence of one of these proteins, it has to be a very pure form. Because you don't have one protein in soil,
Yeah.
you have multiple. And not just that, you have multiple variants of the same type of protein. So let's say you have glycine. When we talk about soy protein later on, we're going to talk about glycine. Glycine has the acidic and basic subunit, and the acidic subunit have multiple genetic variants,
Yeah.
and that can all exist in your extract.
Um,
So the pure meaning completely this one protein, that all of the molecules in the solution have that one composition and one protein.
So the basically what we are working on, like the protein isolates.
No, they're never pure,
Okay.
no. They're pure, when we say about protein purity, is that we only need protein content in regard to everything else, like starch and salt and fat, that's the purity of the protein compared to other components.
Okay.
But when we talk about protein purity for analytical purpose, like sequencing, it has to be that singular protein,
Oh,
yeah. Not an isolate of the mixture of proteins.
okay.
Yeah, good questions. That's it? You don't want to delay me anymore to reduce the number of topics you are gonna cover for the exam? Okay. Good, I like that. Let me ask you a question now. We're gonna talk about functional properties in this lecture today. So, and we're going to relate structure to function. A lot of you already do that in the work that we do in lab. So let's see here. You read it and you give me an answer. Coleman. Yes, that is correct. Are you going to tell me why?
Well,
Yes.
I just kind of got through it. And in the way, listen, hold on, I'm explaining this.
Explain yourself. Explain yourself.
For C, right? If it has a high hydrophilicity,
Yeah,
the emulsion at the center of the emulsion is gonna be the oil. So if you're radiating out the hydrophilic parts, you're gonna need more hydrophilicity to create that micelle than you would
yes.
otherwise.
Yeah, you're right. See, you get it. Where are the pins? Those markers.
I think they're behind the screen.
Why did they do that? Okay. So we're gonna talk about emulsion later on. So we have an emulsion, and in an emulsion, you have your we call it dispersed phase and dispersing phase. So this is the dispersed, and this is the continuous dispersing phase. So if this is water, so it's oil in water emulsion, then you want a lot of hydrophilicity because you have a lot of interaction with the water, and you have also protein solubilized in the water because you want that viscosity to be higher to stabilize the oil droplets and prevent coalescence. So you want good hydrophilicity and good solubility of the protein to cause steric hindrance here, repulsion, and to interact with water and increase the viscosity of the space or the dispersing phase or the space. So when percent hydrophilicity is low, a protein forms a better emulsion when oil is the dispersing phase. So in the contrary here, when you have oil and then you have water, like what food product is oil, water and oil?
Butter.
Butter, yes. So in this case, you have the oil here as a dispersing phase. So you will have higher surface area that would need to interact with the oil. So that would be B and C then. In this case, is good. Okay. All right. Globular proteins can form thick films at the oil-water interface, tend to form smaller, thinner adsorbed layer, can impart extended emulsion stability. Okay, we're gonna talk about all of this, right? But I wanna see your best guess here.
A and C.
Yeah. It's A and C. Okay, we're gonna talk about it again later, but just to introduce it now and then talk about the concept later. Okay, so globular proteins usually have smaller, like overall size than open structure, like say this is casein, this is whey protein. Okay, so these globular proteins will then, do not take a lot of space at the interface. So you want to think about proteins forming a film around your oil droplets. When you homogenize and you disperse your oil, then your proteins are forming this film around your oil droplet. So you will have more protein fit around that oil droplet. If you have casein or a very open structure protein, so you will have, yes, it would form naturally a very nice emulsion, but it might suffer from having a thin versus a thick film. So if you have a thin versus a thick film, this might have suffered from stability. Because thin films will tend to coalesce and fluctuate and then separate, more than thick that will have a lot of repulsion and state hindrance with another oil droplet. So the thicker the film, the better stability you have for your emulsion. Okay. So we, again, like I said, this is our map for what we're covering. We talked about intrinsic factors. We talked about extrinsic factors that changes the protein from nature to denatured. We haven't talked about modification yet, but we talked about changes. And then what we're going to do now is define functional properties and relate structure, intrinsic and extrinsic, to these functional properties. And this is the definition of functional property. So a functional property is any physical chemical property which affects the processing and the behavior of food systems as judged by the quality attributes of the final product. Quality attributes can be visual, textural characteristics that are imparted by these physical chemical properties. Okay, so that's the definition and it's repeated here. And what are these functional properties influenced by? A lot of different things. Okay. So it's a compounded effect. So they don't exist, proteins do not exist in a vacuum. And a functional property is not just influenced by one characteristic. So it is influenced by the composition of the protein, by the structure and configuration, the physical chemical properties, including surface hydrophobicity, surface charge, sulfide group, etc. Other food components, salt, sugar, moisture, whatever it is, carbohydrate, and the nature of the environment, pH, ionic strength, temperature, all of that. So, FYI, you don't want to study, but you want to know. You need to know when we talk about what do we mean by hydration properties, surface properties, structural properties. I don't so much cover organoleptic here or kinesthetic. But we're going to talk a lot about hydration where you have water protein interaction. And then you have surface activities important, surface properties and surface activity that leads to emulsification, foaming, and impact on bonding of liquids, binding of flavor, stabilization. Textural, so when we talk about viscoelasticity, we talk about viscosity, gelation, or the extrusion properties, any rheological properties really related to texture. So it's kind of differentiation of different properties, and under each category you have different functionalities. Okay. Then this is a very old table. I've been trying to find something newer and nicer to show. And if you can tell, all of the proteins are animal-based proteins. So this is really old. We should have a new textbook or book that includes now the plant proteins that are emerging. But so here you have the functionality, and then you have the mechanism. So solubility is impacted by hydrophilicity. Let's look at gelation is water entrapment and network formation, and so on. That's the mechanism. We're going to talk about mechanism for key functional properties, where these functionalities are important. Solubility, beverages, viscosity, soup, water binding, gelation, see the meat products here, and so on. Okay, and then these are the different proteins that will impart these functional properties. Okay, but these are just not inclusive of any plant proteins, so this needs to be updated in the future. But this is just to give you an idea of the different functional properties, the mechanism of action, types of food, and potentially types of proteins. Okay. So there are categories based on interaction with water, and another category based on interaction with hydrophobic environment. So here under interaction of water, so you have aggregation and hydro interactions with water that leads to solubility or leads to gelation, for example, and anything in between. So protein water interaction and protein water protein interactions. So solubility is basically relying on protein water interaction. Gelation, we're relying on water or protein water protein interaction. You want an interaction with water and you want protein protein interactions. And then you have the surface activity where you have interactions that involve hydrophobicity. So emulsification, foaming, flavor binding. Okay, so different structural characteristics have more value or impact on these different properties. So the molecular size and the shape or configuration impacts the viscosity, elasticity, gelation, texturization. So we're going to talk about impact of large molecular weight on the formation of gel on ability to texturize. Okay. In gluten, for example, you have the gluten forming protein form large polymers, gives you that elasticity. But also you have interactions with water. High water binding capacity implies higher viscosity, for example, and large molecular weight will cause higher viscosity. Okay. So surface properties, we talk about hydrophobicity, hydrophilicity, or charge. Charge is not the only thing that causes hydrophilicity. Polarity of the protein, it can be polar. You have polar residues, not necessarily carrying charge, but polar. Okay, so that's why I have here hydrophobicity, but then hydrophilicity can also either or not carry charge. So these surface properties control or have greater influence than other properties on solubility, water holding, foaming, emulsification. pH. Okay. You like isotherms, right? Well, you know. Okay, monolayer, multi-layer, all of this fun stuff. I'm not gonna go into that fun stuff. What I'm gonna just talk about is protein-water interaction in simplified manner. So this is your isotherm, which really is just telling you have three degrees of water activity or three regions. So usually the first region is just below the monolayer or at the monolayer of your water monolayer. Okay, so what happens in that first region? You have very strong interaction with water. So your water is interacting with your polar or charged groups on the surface of your on the protein. And this interaction is very strong. The water is, you cannot freeze it. It's interacting strongly with the protein residues. It's not free for chemical reactions. It is not freezable and it requires higher temperature to evaporate than the bulk stream water. So when we say water binding is the ability of the water to bind to the protein or the ability of the protein to bind large amount of water. Okay, then you have the second region. That's when it starts to form your monolayer and start layering the water. So you start building up this layers of water. And then this is available for chemical reaction and for solubilizing small solutes. And then you have the multi-layer water when you have really high water activity. And that's even more available for chemical reactions. So what does that mean in terms of how we identify protein-water interactions? So you have the strongly bound water, which is under the monolayer. The water is associated by mostly hydrogen bonding and dipole-dipole interactions. So it has different characteristics than free water. It's bound to the different amino acid residues within the protein. You have the entrapped water that is bound in the three-dimensional matrix. And then you have the free-flowing water or hydrodynamic water. So bound water, hydrodynamic water, and physically entrapped water. Okay. So these are the terms that you would want to know. And water binding capacity, which we run in the lab, but not a lot. We don't measure it often in all the projects, but usually it's measured in grams of water per gram of protein, or sometimes it's a percentage. How many grams of water is bound by 100 grams of proteins? Okay, but often it's grams of water per gram of protein, and many times it's large. The amount of water is larger than the 1 gram of protein. So, what is it affected by? It's affected by composition. So this is the equation that shows you the relationship of the water binding with the characteristics of the amino acid. So the grams of water per gram of protein is a function of the charged residue. So you can see here there is 1 factor of 1. Here's 0.4, here's 0.2. So this is charged, this is polar, and this is non-polar. And you can see that water binds to all of them, but it's impacted mostly by the charge. The more charged the protein carries, the more binding of water. And then polar, and you think that non-polar protein amino acids don't bind to water, they do bind to water. Because amino acids have all of these functional groups that still can do hydrogen bonding interactions. So even non-polar residues can bind water, but to a lesser extent. Okay. So the composition is what we talked about, the different amino acids, charged, polar and non-polar. You would think when you denature the protein, you think that, oh, I'm gonna bind less water. No, you're exposing more groups, so you are binding more water when you denature the protein. Temperature also impacts well, if you denature and unfold, you're binding more water, but if you cause polymerization, then you are gonna be binding less water. pH, so if you change the pH and you increase the ionization, then definitely you're gonna bind more water. So ionized amino acid binds 2 to 3 times more water than non-ionized. Salt concentration, you want to remember the salting in, salting out. With salt in concentration, a little bit of salt adds a charge load on the protein and can enhance protein-water interaction. A lot of salt can cause the opposite. And the presence of low molecular weight compounds, so sometimes sugar, acts as enhancing protein-water interactions. You remember what I showed last time in the fourth lecture, this figure that differentiates between cosmotrope and catrope. So the cosmotrope, so sugars, small sugars like sucrose or glucose can act as cosmotrope. So they will cause the protein to interact more with water. Whereas catrope, they will bind strongly with the protein and prevent them from interacting with water. So different salts can either be here or here. And thus they might have different impact on water. So this is just examples I pulled from different research papers. This should be SPI, I don't know, it's a typo. But you see that when you increase temperature to a certain extent, you're getting more water binding, and then you reach the plateau, and then you start seeing polymerization, and that would reduce the amount of binding. For casein, you don't see much change because it's not impacted by the low temperature like that. So there's no structural change, so you won't see a change in water binding for casein with temperature less than 130 degrees C. Salt, depending on the salt concentration, and then as you increase salt, you might see an enhancement. Then you're going to see a plateau, and the curve does not show you what happens later, but at some point at very high concentration, you're going to have the opposite effect. Here's the pH effect. Same with the solubility curve. It's very correlates really well with solubility, where you have enhanced binding when you have charge, and under alkaline conditions, you have more binding water. You remember? What's that? We have more residues that become negatively charged, not just your carboxyl groups. So you will have your carboxyl groups. Your amine will lose its proton, so it will not carry a charge. And then your SH becomes S minus, and then your OH becomes O1. Under alkaline conditions, you have additional groups that will carry that charge, but under acidic conditions, only your NH3 and then your COOH. So you only have this that contributes to the net positive charge. That's why for water binding and solubility, we see it more at alkaline conditions. We never solubilize protein to extract them at acidic conditions. We use above pH 7 to extract our proteins. All right, now you tell me the difference between water binding capacity and water holding capacity. And then in literature, it bothers me so much. Huh? What's that?
People who are our meeting.
Yes, what did I tell you?
Yeah, they keep on getting it mixed up.
Yes,
When
it's
they're
so
not.
annoying.
It's more about how much the protein in like in trap, like the protein interaction and the water binding inside the protein in water.
Yes, exactly. So water holding has to do with forming the gel.
Yeah.
So you're holding the water within a matrix, whether it's thermally induced or acid induced or whatever induced. You are holding the water within a matrix. And we usually couple it with gelation because it's the better the gel, the more holding of the water, the less is the synergesis. Water binding is directly related to viscosity, for example. The higher the water bonding, the more viscosity building you're going to get in your food application. Okay. Good. Who's gonna boo this? What? Okay, so who will what functionality does not need solubility? Yeah, I'm gonna say opposite of what I'm saying over there. What functionality does not require the protein to be soluble at least at pH 7? Yeah, go ahead.
I don't know.
Yeah, I'm gonna say something. Say it. I'm not gonna laugh at you.
Extrusion?
Yes,
Is it really?
gluten is not soluble at pH 7, but it extrudes well and gives you that wonderful structure, meat-like structure. So solubility is not a necessity for extruding properties or extruding potential. But you want, for extrusion, you want the ability to form stable polymers, not necessarily aggregates, but forming the polymers during the extrusion. You don't want to start with a protein that's already aggregated, like pea protein, terrible, aggregated, poor. It's not going to extrude well for you. You want the protein to polymerize during the extrusion process to form these fibrous stuff. So here, degree of solubility influence other functional properties, but not necessarily the extrusion properties. Okay, so we want the protein to be soluble. If it's not soluble, you're not going to get your nice emulsion or foam or gel, and obviously not feathery. Whenever there is an aqueous phase, you need the protein to be soluble to some degree in order for it to interact with the aqueous phase. So with lower solubility, overall functionality is reduced. That's why one of the key things we first measured and then that you booed is solubility. So it can definitely be an index of denaturation. When we lose solubility, that's an indication of the protein not only denaturing but forming polymers. It's very much influenced by the environment. Okay. So when proteins have overall higher percentage of hydrophobicity, large percentage, over 30% hydrophobic, then the protein is less soluble than other proteins that have less hydrophobicity. That's why plant proteins in general are less soluble than animal proteins because of the fact that they have high percentage of hydrophobicity. And that's what makes them form these large quaternary structure. So 11S, a hexamer, so it associates, whereas beta-lactoglobulin is a monomer or dimer, depending on the pH. So when your plant proteins are forming these large quaternary structure, they're basically because of this high hydrophobicity. So in general, when you have high hydrophobicity, solubility is lower. when you have higher charge, solubility is higher, so it's not saying anything surprising here. Both surface hydrophobicity and surface hydrophilicity have a direct bearing on solubility. So it's not just what's the surface hydrophobicity is. You want to look at, sometimes you have some surface hydrophobicity, every protein has hydrophobicity on the surface. But if they have a lot of hydrophilic groups and charges, then you have a nice balance that would give you the solubility or enhance the solubility. Okay. Solving in, solving out, we're going to bring it up in so many different scenarios. So we talked about, having, sometimes you add a little bit of salt to beverages to enhance the solubility, such as phosphate in protein beverages. So what it does is adding charged load. So when you have proteins that could be potentially interacting via isoelectric interactions, ionic interactions, and then you have the salt is going to add charge load and prevent these proteins from interacting with each other and have them interact more with water. But above a certain concentration, there will be a lot of shielding of charges that will counter this effect and prevent the protein from interacting with water. And normally we say salt concentration, but ionic strength is the better term to illustrate the effect of salt, because it takes into account the charge, the amount of charges, not only how much the actual molecular concentration, because different salts carry different amount of charge. So the ionic strength takes into account not only the molar concentration, but also takes into account the charge, like divalent, monovalent, or what have you, in terms of the salt. So yeah, salting out is that shielding of the charges that can also cause even intramolecular interactions, cause potentially unfolding, enhance hydrophobic interactions between the protein, compete for water, and reduce the solubility of the protein. pH effect. So this is not rocket science. So when you have more charge, net charge, whether negative or net positive, you enhance the solubility. When you're around the isoelectric point, that's when you don't have repulsion, and that's where hydrophobic interactions dominate. When you don't have repulsion anymore, hydrophobicity on the surface dominate the interactions, and you will have less interactions with water, and you will have less solubility. So we have differences in the impact of surface solubility, surface hydrophobicity and solubility. So we have your golden standard for solubility, and then you have plant products, illustrated by so. So let's look at this figure, what that means. So this is pH, and just take that as percent solubility, where they're measuring turbidity or transmittance. So the higher the transmittance, the lower is the turbidity, the higher the solubility. Just consider that as solubility. Okay, so native whey protein, that's square. No matter how you change, what's the isoelectric point of whey protein? 4.5, 4.6. It does have an isoelectric point. But what do we see here? Even at its isoelectric point, it remains almost 100% soluble. It's wonderful protein. Why? I see a confusion on your face. Yes. But can you tell me why then? Oh. Structure, what's with the structure? Open? No, go for it, so you know it.
Yeah, whey protein.
What's so unique about whey protein that we probably mentioned maybe once or twice or 10 times? What's so unique that makes it a golden standard for solubility? It's small, yes, it has a molecular weight of 16 to 18 without it, not too, but small, but that's not the main thing. What's so unique about it? I'm not picking on them, that's trying to show you that you know this.
It's not long.
It is globular,
It is.
yeah. It is globular. It's very globular.
It has ever.
It does have hydrophobicity, but what's unique about it on the surface? It has, okay, common one.
I was thinking of casing,
Yeah,
Okay.
that's what I was.
yeah.
Okay, so yeah, they have similar isolectic point, but whey protein is soluble if it's not needed. So that's why you can form cheese at 4.6, whey protein is still soluble, although it's isolectic point. Why? I did say it once. Who's gonna be the one that gets +3? Who's today? Instead of +2. Nobody's gonna get +3 today, what? Composition. Yes, it has to do with composition, but what's the
More.
hydrophobic residues? More hydrophobic residue where?
Inside.
In the insides. So thank you, Abby, it has to do with hydrophobicity, but it's like you have a location or two and everything else is charged, not negative charge at pH 7. So, and at isoelectric point you have 0 net charge, but we said at the isoelectric point, hydrophobic interaction are dominated, but if you don't have a lot of hydrophobicity, you won't have a lot of attraction. So the protein remains soluble because you don't have enough hydrophobicity to drive those proteins to come together. Because it's a very hydrophilic protein on the surface, regardless of the charges that it carries at the pH. So that's what makes the whey protein so unique, is that it's soluble even at around its isolectic point. However, heated. Once you heat it above 70 degrees, poof, denatured. All of the hydrophobicity now is exposed. Now lose that charge, then you have that driving hydrophobic interaction that you see a steep drop. It's steep though, it's not broad as terrible as plant protein. It's very poorly soluble over a wide range of pH because of the high hydrophobicity anyway. So here you see a sharp drop around the 4.5 mark. And then when it is charged, solubility goes back to 100%. So that's what's unique about whey protein. And that's why we love it. And that's why plant proteins suffer in comparison because of this chart. Heat, no heat, this is the solubility. And it becomes worse when you heat. And you have an overall low solubility. Look at pH 3.4, for example, when beverages are for acidic beverages, you really have poor solubility. Why? Because hydrophobicity dominates these proteins. So you really need to have excess charge to prevent hydrophobic interaction and enhance water interaction. So that is relating structure to function. And that's what we like to do.
So what people say about that, it's because of not enough.
Not enough, not a lot of hydrophobicity on the surface. So there is not enough pull, attraction, like gravity pull, gravitational attraction. Yeah. Okay, and this is the sad solubility of plant proteins compared to whey protein. And we measure solubility in our, yes,
So at isoelectric point, only hydrophobic interactions are mediated.
mostly, yeah, because you don't have, yeah, you have electrostatic interaction, but you lose the electrostatic repulsion that drives those proteins not to come together and interact instead of water. Yeah. And then hydrophobic interaction facilitate disulfide linkages. Why? Because now they are in proximity. So free sulfide groups will now interact and form disulfide linkage. But the driver to bring those proteins together is the hydrophobic interaction. Okay, so yes, so when we run solubility in our lab, we run it at 5% protein. Why? It's not related to this, but why?
Because that's the minimum amount of protein you want in a beverage or like.
The minimum amount of protein to make a clean. And especially for, let's say, proteins that don't have PD class of 1, let's say P has a PD class of 0.8. And FDA requires a 4.2% of protein available to play in high protein zone. So if you have a 0.8, you need 5 grams and 100 grams of protein to play. So that's why we measure at 5%. It's not a magic number, it has something behind it, which is beverage temperature. So yeah, so it is really, really sad for these plant proteins at this around 3.4. Yeah. So what do they do in industry? They add stabilizers, because now when you have poor solubility, you can't add your 5%. And what you can't make that claim. So in order to make that claim, whether it is a pH, a neutral pH even, usually they add carrageenan, and then they add pectins to stabilize at acidic pH, to stabilize. So you add hydrocolloids, basically to stabilize your beverage. Otherwise, in a very short period of time, you have this separation, which if you are a consumer, you don't want to buy this, you want to buy something. So, all right, so this is usually I put the reference here. This is from my first PhD student 10 years ago. But I always like to give that example because it's showing you whey protein and showing you a glycated whey protein. So if you look at whey protein at pH 7, 3.4, around its isoelectric point before you heat, you have wonderful solubility, you know, above 85% soluble. Okay, it's a little lower around the isoelectric point, but still high enough. Heat it. Once you heat it, so, you know, the solubility drops. It becomes 4% soluble. That means most of the protein precipitates. Now, why is this important? When you have acidic beverage and proteins are buffers, so what happens to that acidic beverage when you drink it? What does it taste like? You have protein, 5% protein, and you want the pH to be 3.4. So what did you do? Since it's a buffer, what did you do to keep the pH?
They have a soapy base, we add buffer, maintain the pH, so there's already acid when you add a base. So
No, we're not adding base, we're adding acid, but as a buffer, you add acid and the protein keeps bringing the pH up. And then you keep adding acid, then the protein keeps bringing the pH up. And then you add acid to bring it to 3.4. What happens now to the flavors? Sour and astringent. So we were designing this work to see what is the beverage where you can consider is acidic and require mild pasteurization? What would be pH for mild pasteurization?
That's from his boss.
What is considered pH that would be enough to kill your pathogens? 4.6. So anything less than 4.6, you don't need very adverse heat treatment to make it pasteurized. So if we can build a beverage around pH 4.5 and keep the protein soluble, I would need less acid, right? And I still would need mild pasteurization. So the target here is whey protein is great, but I don't want this acidity and astringency. Can I formulate at pH 4.5 and still have the pasteurization for acidic food? How can I do that? We glycated the protein. So when we glycated the protein, it resisted denaturation. And when whey protein is not denatured, it's very soluble. So it's not denatured and it remained 90% soluble at pH 4.5. So that was a great finding. We were so happy to publish the work. Does anybody do glycation? Nobody does glycation. Why now nobody's doing glycation?
Not commercialized yet.
It's not commercial. Why is it not commercialized? Because you haven't worked on it yet. Because we need scaling, we need feasibility, we need to figure out ways to make it cost effective. It's great from a functionality perspective, but it's not yet feasible from a cost perspective. Okay. Really, you didn't tell me that. I didn't give you a break.
There was a great point to start, so just let me know.
What? Okay. Or you're so engaged. All right, I'll give you 5 minutes.
I told you. I have to.
And then oh, I'm very nervous.
Oh.
Yeah, I did. I was going to tell you.
Yeah, you can.
About the ice cream.
Yeah.
Yeah, I did get a acceptance.
Oh, good. That's good. I'm collecting responses to know how many posters I would have to do in July.
But yeah, I was saying, so I didn't even check my email yet, and I was like, how many people here talked about this already? And then like an hour before you sent that email, I'm done. I just need to have time to check my email yet.
And then you can send the forward right away when you start.
So, do you want me to forward?
No, I don't want to forward. You should tell me right away.
I did, I just saw it. Just told me. I saw it right before class. It's back.
Okay.
Same with Brittany.
Yes, she told me.
Oh,
You were the last one to tell me.
sorry.
So, this one is sugar. Is that the same situation as the salt? No. So you have a lot of, yeah, if you have a lot of sugar, then yeah, they will compete anyway. Whenever you have a high amount of sugar.
Yeah.
Compete with water.
Okay, so for like the little bit amount of sugar.
Well, we have a lot.
Okay, yeah, same thing, chart.
Yeah, it's gonna add hydrophilicity, so it will interact via hydrogen interaction with the protein, and then it adds hydrophilicity.
Okay.
And looses the action, not stronger than because it's full of water.
It's just a lot.
Yeah, but I know. I mean. I know, but that's. Who even do this word? I know, it can be a little. I'm happy we have that space though now. It's massive, yeah. We showed me, and I'm like, is this gonna be enough? I'm like, I mean, yeah. Yeah.
Okay. We have everybody. Okay, we have everybody back. Let's continue our exciting discussion on solubility. Okay, so then we wanted to understand what happened. Why were we able to see this increase in enhanced solubility at the isoelectric point? And then we looked at surface hydrophobicity, and we found that with glycated protein, you had an increase in surface hydrophobicity at 10 minutes of heating time, but then it plateaued and did not increase anymore compared to the regular whey protein. So again, this tells you that hydrophobicity is the driver in the reduction of solubility. So the non-modified protein denatures opens up, the glycated protein resists denaturation. And another thing we looked at is we measured actually the isoelectric point, and we saw a shift. The isoelectric point of the glycated protein shifted to a lower PI. Why? Because when you glycate, you are, it's a Maillard-induced reaction. So the carbohydrate is reacting with an amine group. So you're blocking a potential positive charge. So you're increasing the net charge that caused the reduction in the net negative charge. So that caused a reduction in the isoelectric point. So the protein around the it will be more negatively charged at 4.5, 4.6 than the non-glycated protein. So there's a charge effect, and there was structural configuration effect. So sometimes you have pH salt interaction. So the salt effect is also impacted by pH. So depending on the pH, you have a lateral, like what you call it, the curve shifts. You have a shift in the solubility depending on salt concentration. So at a particular salt concentration, you have different solubilities at different pHs at the same salt concentration. And at the same, similarly at the same pH, you have different solubility as you change the salt. That means that salt impacts the charge and pH impacts the charge. And when you have both of them at play, they're both going to affect your solubility. So depending on how much salt you have and how much shielding of the charge you have, then you will have another impact if you change also the pH. So they're interrelated. Okay. Temperature has an effect. So usually when at warmer temperatures, you have better solubility because of the thermodynamics. With the exception of beta-casein. So I give you this example because if you put milk in the fridge, which you always put milk in the fridge, but when you put milk in the fridge, some of the beta-casein solubilizes out of the casein micelle, and then you will have some beta-casein in the whey component. Okay, so why do you think at refrigerated temperature, beta-casein is solubilized out? There is a hint in the question. What word you think is the hint? Great, so you know the hint. Okay, so what happens to hydrophobic interaction at cold? The opposite. So hydrophobic interactions are reduced at lower temperature. So it is a hydrophobic protein, so it's interacting in the casein micelle via hydrophobic interaction. That's how it's stabilized within the casein micelle. You bring the temperature down, your casein loses some hydrophobic interactions in the casein micelle and sneaks out of the casein micelle. So that's an exception. Okay, above 40 degrees, depending on the protein you're working with, you start having some denaturation. And then that's when we start seeing a decrease in solubility. Sometimes you run, but that's different for different proteins. Sometimes you run protein solubility and you find that protein solubility actually enhanced after heating. You're at 80 degrees for 30. And that happens sometimes with soy protein, sometimes with pea protein that is not already denatured, because it just did not reach that high denaturation temperature for these plant proteins. So it actually enhanced its solubilization rather than cause a decrease in solubilization. So it's really that 40 is just not a fixed number for all of the proteins. Again, Buddhists, right? You all know how to measure solubility, most of you. We've done it in the lab multiple times. So when we talk about functionality in this section, I tell you what the method that we use normally. And here you just prepare your protein in water or buffer, adjust the pH, add salt sometimes to see the impact of salt. And you let the protein disperse, and sometimes for an hour, sometimes for 2 hours, to make sure that the protein is well dispersed and solubilized. Then you apply a centrifugal force. Do we do 30 minutes? 10 minutes, okay, so 10. And then what you do is you will have a precipitate and you have the soup. Before you do the centrifugation, when you are stirring, you take a sample and you measure the protein content in your solution before you do centrifugation. You vortex really well, the protein is well dispersed so that you can get the total protein in the dispersed solution. Then you centrifuge, then you take the supernatant and you measure protein in the supernatant. Then you take the ratio of protein in the supernatant versus total protein that you got from your wonderful LECO instrument, usually, and that multiplied by 100, that gives you the percent of protein that was remained soluble. So it's prediction of behavior in the beverage. The higher the solubility under these conditions, the higher potentially the inclusion level that you can have, and the higher the stability of your beverage on the shelf. And it's always comparative, right? It's not an absolute value. You always compare it to different proteins. That's why a lot of times you have reference proteins, just to have an idea of how your protein fares in comparison to other proteins. Okay, moving on to gelation. Any questions? Okay, you're experts in solubility. All right, so the gelation, basically a gel is, or gelation is the ability of the protein to form a gel in an aqueous solution, usually. So the gel is a three-dimensional, a solid-like network of protein entrapping water. So there are different forms of gels. Yogurt is a gel. I don't have it up here. This is a tofu, this is jelly, a hot dog, the egg white. These are all different forms of gels. So water is dispersed, and then your continuous phase is your protein maintenance. Sometimes gels can be formed at 1% protein, like gelatin, but sometimes they need 20% protein, right? Proteins. Yes. So depending on the protein, they can have good gelling versus poor gelling ability. So how do we usually assess gelation properties? Whether a protein can be a good gelling agent. Okay, so that like before that. What is a determinant? Also a hint on this page.
When we take it out of the fumes, the factor failure to hold
These gelation concentrations. I don't have it here, but I just thought of it. Is that the lower the percentage of protein that we use to form a gel, the better is that protein as gel. So these gelation concentration is very important. That's one characteristic. That's why I have here the 1% as a reference, but then you have whey protein forms a gel at 5%, soy protein forms a gel at 10 or 12%, then pea at 20%, or maybe 15, depending on the source. So to form a gel, the first thing you want, what happens is you have the protein, you want it to be denatured, you can induce denaturation mostly via heat treatment, and then you form soluble aggregates with a continuous heat. You start forming the soluble aggregate,
and the soluble aggregates start forming a network, and the water is embedded within that formed network.
So you have thermally irreversible gels, and these are the most common gels. They are stabilized by disulfide linkages. Egg white are high in sulfidal groups, so you would have an irreversible gel form. You cannot resolubilize your egg white once it's formed. Usually proteins that form high molecular weights. Either they are high molecular weight themselves, or they form high molecular weight quaternary structure, or when we form soluble aggregates, then you have a better chance of forming a gel. And when you have really high degree of hydrophobicity. So when you have high degree of hydrophobicity, really large molecular weight, and disulfide rigid, you are forming thermally irreversible gels that are maintained upon cooling. So thermally irreversible, the most common example is your collagen. So this is your native form collagen. It's stabilized mostly by hydrogen bonding. There is some disulfide interchange too, but mostly hydrogen bonding. So hydrogen bonding is weakened by heat. So when you heat, you break the hydrogen bonding, and then you form this irregular forms, coils. When you cool, hydrogen bondings form again, but then they don't go back where they were. So you have your denatured collagen is gelatin. When you cool, you form that gel. If you heat again, you break those hydrogen bonding, and it goes back to soluble. This can become irreversible if a strong disulfide linkages occur, then the gel will not go back to be solubilized. So a process. So you have the protein, you heat to induce unfolding or denaturation. Then with more heating time, you start forming your soluble aggregates. With more heating time, you start forming the network, the gelling, forming your matrix, and reaching equilibrium. So heating time and temperature is really key. And heating above the denaturation temperature of the protein is really key. If you have soy, for example, and you heat at 70 degrees C, it's not gonna denature for you, it's not gonna form a big gel for you. So protein properties that impact gelation molecular weight. So when you have small peptides or polypeptides, they don't tend to have good gelling behavior unless they have specific characteristics, high hydrophobicity and high sulfidal groups. But in general, low molecular weight proteins are not good for gel formation. So when we talk about the interactions, so this is just to remind you that as temperature increases, hydrogen bonding and electrostatic interactions weaken, hydrophobic interactions increase, disulfide bonds are enhanced, especially at alkaline pH or above pH 7. Sometimes mixture of proteins enhance gelation, and different proteins gel differently. Alpha-lactalbumin is formed gel, but not as strong as beta-lactoglobulin, because beta-lactoglobulin have a free sulfidal group in the middle of the molecule that initiate disulfide interchange. Mixing proteins improve gel, so you often find that yogurt, they add whey protein to yogurt, because whey protein can interact with catechosin, their disulfide interchange, to enhance the gelation and reduce syneresis of the yogurt over storage. So holds better the water. So protein concentration is important. So like I said, gelatin 1%, whey protein 5%, soy protein 10%, etc. So the protein concentration is important for forming the gel. pH. So what happens to the gel formation when you have extreme alkalinity or extreme acidity? You don't have a gel, it's very, very soluble. So here, as the pH approaches the isoelectric point, and as you increase ionic strength. So we look here at very high pH, your protein is really, really soluble. Reduce the pH, then you start forming gel. As you approach the isoelectric point, you start to have grittiness and turbidity. Why? Because you start forming what protein aggregates. So you will form a gel, but it will have a gritty, turbid texture. Okay, so you want to be somewhere in between here where it's not close to the isoelectric point and not too high above the isoelectric point. So somewhere in the middle, but that differs. The pH and salt concentration differs for different proteins. So you need to have optimum pH and ion strength depending on your protein source. But that's the general trend. You get close to the isoelectric point is not good. Very far away is not good either. Calcium ions or divalent ions sometimes are added to enhance gel formation. So think about what application calcium ions are. What can you think of? In what application? Yes, so cheese formation curd. Sometimes you add calcium ions to your milk during the formation of curd to enhance. Where else we're adding calcium ions? Another application. Very common. No. Baby formula. Baby formula. You want to form gels and baby stuff. Pectin? Oh, pectin, yes, but in terms of protein, yeah, we use that to enhance the gelling capacity of pectin, yes, but for protein. Yeah, but what very common application?
Yogurt.
Yogurt. Yeah, it could be added yogurt, but I was thinking of non-animal based. Tofu. Tofu is the main ingredient in the formation of tofu. Yeah, great. Heating temperature and heating rate. So, like I said, we need to heat above the penetration temperature. Every protein is different, so we want to hit that mark or make sure we get that mark. In our lab, we always to 95 degrees. But the heating rate also needs to be controlled. Because you don't want a solution to reach high temperature very quickly. You start forming aggregates rather than nice, slow change in the protein and slow matrix formation. So heating rate is very important. Heating temperature is important. Proteolytic enzymes. So you want to make a jelly with pineapple. Do you use canned pineapple or do you use fresh pineapple? It's a common question you undergrads, when you were undergrads, I'm sure your process or just chemistry class. Huh? You want fresh? Yeah, why? I mean, I love fresh, but why do you want fresh? Enzymes. Do you want the enzyme to form the jelly? Oh, it's the opposite. So you have bromelain in pineapple and it's a protease. If you try to make a jelly with fresh pineapple, it will never form because then it's going to break down your proteins into less than 10 kilodalton proteins, peptides. So it won't form.
So you want canned pineapple?
So canned pineapples. So you want canned pineapples. Not that I'm expert in jelly, but that's the common example. Sometimes the sugars and polysaccharides, again, at specific concentration, add that viscosity, adds that, enhance that gelation of holding water and trapping water. All right, so here is linking structure to function in proteins that you guys are, most of you, I shouldn't say all of you, most of you are familiar with, like semolina protein. They have relatively low molecular weight proteins compared to soy. Okay, so soy protein have all of those large quaternary structure proteins, and even when you break them down into their subunits, you still have subunits that are high in molecular. So when we look at the gelation, there is a vast difference between camelina protein and soy protein. A big part of it is the molecular weight of soy protein. All right. Even more, when we look at pea and soy, we look at not only the molecular weight, but we look at the profile. Soy has high amount of 11S protein, a large molecular weight quaternary structure that has disulfide. Whereas pea protein has less proportion of that 11S. It's called glycine in soy and referred to as lignin. When we cover lignin protein, we talk about this more detail. But just the proportion of the specific fraction is different. Now, from Holly's work, we learned that it's not the only factor. There's more to the story, but the profile and the composition impacts the gelation. And we know that soy forms, this gelation is at 10%. Pea does not form, and sometimes it forms a weak gel at 15%, sometimes it doesn't, depending on the source of the protein. So composition and different proportion of different fractions impact gelation. Here's an illustration of different protein sources and their ability to form gels. Here's your whey protein. You're surprised it forms a stronger gel than soy protein. At 5%, you can form very nice, strong gel matrix, and then it goes downhill for plant proteins after soy over there. Like if you look at rice protein, it has 70% protein, it doesn't form a gel at all. Low molecular weight and no sulfide groups. So where does, if we went to today's trend to having plant-based daily, and you look at plant-based cheese, this is cheese made with pea protein. What are we looking at? Images with microscopy, confocal laser scanning microscopy. And with this microscopy, you can stain your components. So red is for fat, green is for protein, and blue is for carbohydrates. So in cheese, you see a very nice protein matrix, a very nice gel entrapping those oil droplets in there. In vegan cheese or plant-based cheese, what do we see? Bits and pieces of the green. They really add very minimal amount of pea protein anyway, just to say we have protein in there. But then you see the blue, lots of hydrocolloids. So plant-based cheese is stabilized by different starches and hydrocolloids. Protein barely has any role. You don't see any gel network in comparison to cheese. How do we measure gelation properties? Here's your water holding, you form a gel, and you invert your cube, and you determine the weight before and after at certain time points to determine how much water was lost. So there is a long equation that you would apply to determine water holding capacity, but it's really based on forming a gel and determining how much water is released. The less water released, the higher is your water holding capacity, and usually it's a percentage out of 100. You can do it in actual food products to look at the water holding capacity. And this is a beef patty. This is without adding whey protein, and here is adding whey protein. So the addition of whey protein helps with holding water and preventing this loss of water and actually loss of fat during cooking. So you can test that by actually, you want to look at adding, one of my former students did that with a beef patty and using whey protein. So you add your mix and then you determine fat and moisture, and then you cook. you let it settle, and then you measure the water and oil separated, and then you can calculate water holding capacity in an actual food matrix. We determine rheological properties of the gel. We don't do that in our lab. I'm not a rheology person, but usually when you read papers, sometimes you read G prime and G double prime and all this that I don't like, so I don't do it. But it's basically looking at shear stress and shear strain, and at different values, you can determine whether your gel is brittle, is rubbery, is tough, is mushy, and so on. But what we do in the lab is measuring the strength of the gel using our temperature analyzer. So you form your gels in your little tubes, centrifuge tubes, and then you use the right probe and the temperature analyzer that goes down and compresses the gel, and you measure the mass or the weight, and you convert that to force in Newton. And the higher the force needed to compress your gel or break your gel, the higher is the strength of your gel, basically, and the better is the gelation property of your protein. And usually when we determine the least gelation concentration, we make sure that we prepare the solution at higher than your least gelation concentration, so that we can form a relatively strong gel and have a comparison between different proteins at a particular protein concentration. Emulsion. I'm determined to finish this topic, so it's included in the exam. All right. Emulsion. So what we have here is when you mix oil and water, you have surface tension. You have a tension, you have difference in the density, and the more difference you have in density, the more you have tension. So, and the emulsion can be oil and water or water and oil, and oftentimes it's oil and water emulsions in most applications, at least in foods. So you have the dispersing phase, and then you have your dispersed phase. So if it's water or oil and water, you have your oil droplets in the water, or the other way around. Okay, so, and in foam, you have similar idea, but then you have your aqueous, and then you have the air. You can also have foam in lipid phases, but mostly, again, when you talk about ice cream, for example, you have the aqueous and you have the air bubbles in between. So, in terms of the protein, when you have oil and water, let's say, you shake, you put the oil and water and you shake, you will see little oil droplets forming, but soon they will see separation. Oil goes on top, water goes on bottom. There's nothing to prevent that phase separation. But when you have a protein in there and you homogenize, you're not only breaking down the fat into small oil droplets, you're also causing the protein to unfold and to orientate its different hydrophobic and hydrophilic groups to the aqueous and to the hydrophobic region. So if you have water, the hydrophilic region of the protein will be orientated to the water, and the hydrophobic will be oriented to the oil, and then protein interactions happen. They form a film and they stabilize those oil droplets, basically. Yeah. So this is basically what I said. It's entropy driven, meaning you want to contain any energy. You unfold, then you contain the energy generated by unfolding and forming interactions and forming that film around the oil droplet. So you always need the homogenization. So homogenization, education without any surfactant or an emulsifier, you will get phase separation. But when you have protein and you have the agitation, the homogenization, then you get this form. You will have that layer, stabilizing emulsifier layer around water or oil. And then you have different components of the protein orientating to the different phases. So basically with the agitation and with the protein, your idea is to reduce surface tension. And then there is a relationship between surface tension, the work that needs to happen to reduce the surface tension. And then you have a great increase in surface area when you have those oil droplets, then you enhance the surface area with forming. The smaller the oil droplets, the better is the greater is the change in surface area. Decreases the diameter of the droplet and disperses the homogenization, helps with increasing the interface area, basically. And then here, the emulsifier stabilizes our protein, or in some cases, we use surfactants such as lecithin, phospholipid that is mono and diacetyl. This is the famous phospholipid structure. So here, this diagram, what it's showing is this is from Fenner level. It shows that the white circle is high hydrophilicity, the black is hydrophilicity. So when you have a protein that is very hydrophilic on the surface and it's not denatured, it will not absorb at the interface. It will not be wanting to interact with the hydrophobic phase. If you have some hydrophilicity, you have some interaction or absorption. We call it absorption or adsorption of the interface. When you have higher surface hydrophilicity, you have more probability of absorption at the interface. So a lot of time we hear, when we talk about emulsion, we hear surface hydrophilicity balance. Okay. Or sometimes it's called hydrophilicity, like hydrophilic balance, or HLB. You will see that thing term sometimes if you're reading manuscripts. You will see HLB. That is hydrophilic lipophilic balance. I often say hydrophobic balance, but this is another term that we would find when we're reading literature. Okay. So there are certain mechanisms that needs to happen, or processes that needs to happen. So your protein needs to be able to quickly go to the interface. So this time in the lab, this is measured by amount of activity, how quickly the protein can get to the interface. And then you have how flexible is the protein to unfold and orientate. And then how well the protein can form two-dimensional organization to have protein-protein interaction and form the film around your droplet. I'm so sad. Okay. Well,
Good attempt.
huh?
Good attempt.
Yeah. So whatever I covered up to here, and I'll try to make sure the exam doesn't cover anything afterwards. All right. I will see you when I see you. Study well and have a great break next week. Oh, really? No.
Yeah, my little baby